Yeah, can you confirm if my screen is visible?
Yes,
Yes,
sir.
sir.
Yeah, okay. So in between, if you have to ask any question, you can ask. So today's topic is your regression analysis. It's in your unit 2. Okay. So coming to this regression analysis, I think this is typically the first ML algorithm, and it's a kind of, you can say, the basic machine learning algorithm which people start to know how machine learning algorithms works and how they typically predict, okay, using some of the continuous variables. So outcome of this regression analysis is always your continuous output. So there are two different types of you can say machine learning. Typically one is classification and other one is regression kind of analysis. Okay, in classification typically we predict some binary, or maybe you can say a tertiary kind of output, but majority of the time binary. Let's say for example, if you want to give loan to particular person or not, denying an acceptance of a loan, so this kind of a thing will fall under your classification algorithms. Okay. So what we will try to cover, we'll try to cover what regression analysis is, and there are some assumptions of this regression analysis, and we'll try to model it uh, in the class. Either I'll use R or Python, but let's hope if I get some time I'll use it Python, or maybe in the next class I'll show you how to code it. Okay. So there are different, you can say, the KPI of this regression analysis. Typically we come across, for example, some terms, some key terms in regression analysis. Is first obviously the regression, the line of best fit. So if you might be asked in interview, what is line of best fit, R squared, sometime what is SSE, sum of squared errors, multicollinearity. So these terms, multicollinearity is related with how two, you can say, variables are collinear. Okay. So, and there is something called VIF, that is variable inflation factor. Okay. I'll let you know what is this. And there are some terms called tolerance and OLS. So it's a least square. So I'll let you know what is this. Okay. So these are the some, you can say, the important terms which you come across when you read this regression analysis, and it's nothing but it's a basic machine learning algorithms. Okay. And you all know what is machine learning, so I'm just skipping it. So, and I have shown you all these things, the machine learning part, the supervised, unsupervised, semi-supervised, reinforcement learning. So we are here, the regression part, the linear. There's something called a linear regression, multiple linear. Linear means we have one dependent and one independent variable, dependent and independent variable. If you have a multiple linear, it means we have one dependent and many independent variable. Okay. Polynomial means obviously it will follow certain kind of a parabola. Okay. So that is called a polynomial regression. Okay. And then comes this classification algorithm. So in coming class we will cover some logistic regression, some decision tree. We will see how classification can help predict, okay, finding patterns in the data, and through unseen data how we can find and how we can predict. Okay. So deep learning is not part of our syllabus. Okay. So this is all. And typically we see this machine learning versus this classification, you can say the classical programming. So if you can recall it, during your C++ programming, we give some rules, you can say some codes and the data to the machines, and then machine gives you some answers. That is your output. Okay, but here in ML we typically provide the input and the output. Answer is output and data is input.
सर बच्चे रिक्वेस्ट भेज रहे हैं, एक्सेप्ट कर लो.
1 minute, I can't see. Okay. Oh. Everybody's in. Okay. Yeah. So so typically in machine learning, I'm just revising it. Data is nothing, your input, and answer is output. Okay, input and output combination we provide to machine, and machine gives you some algorithms. Rules is nothing but algorithms. Okay, so that is a typical difference, because whenever you change the input, your rules will be modified as per your output and everything. It will adjust to machine learning. Okay, but in traditional programming we have to rewrite it again and again. Okay, because every time you tweak the data, you have to tweak the algorithm as well. That is your rules. You have to change the rules. But here, based on data and the output, the rules will be easily governed. Okay, so this is just extension of your previous pictorial, so it's nothing, it's a similar one. So just see, in the machine learning you just pass this training input and the output. Okay, you just train your model, so whatever logics comes, that is your algorithms. And this input, this is unseen input. Okay, so whenever you pass unseen input to the trained model, this will predict you something. Okay, so this is typically your machine learning works. First you train a model, and then you test it through unseen input, through the unseen data. Okay, so this is how our you can say the ML models typically work. Okay, so now comes to this regression analysis. So regression means there are different regression techniques. So it's a method performed to estimate the level effect of an independent variable X. Let's say you have one independent variable. Let's say you have a sales data, and corresponding to sales data you have revenue data. Okay, let's say 10 years of you have a sales data, and corresponding to that sales data you have revenue data. Okay, so let's say sales data is your independent variable and your dependent variable is revenue. So regression analysis is statistical methods performed to estimate the level effect of an independent variable on dependent variable. What is effect of independent variable on dependent variable can be calculated using this regression analysis. Okay, so it helps us to estimate the contribution of independent variable on dependent variable. Means what is the contribution of, let's say, sales on revenue. So you are just trying to find out the contribution of every single, you can say, the independent variable on dependent variable. What is their contributions? Okay, that is called a regression analysis. So it's just an, if you have one independent and one dependent variable, then we will say it's a simple linear regression. Linear means if you are moving one data in X direction, Y will also move in X direction, maybe in positive or negative. Okay, that is a linear. If you have a 1-to-1, that is one dependent and one independent variable. Okay, but in multiple, as I already said, there will be one dependent variable and many independent, more than one. That will come as a, we call it a multiple linear regression. Non-linear means it will follow some polynomial graphs. Okay, so this is how you can define a regression analysis. This is just a contribution of independent variable on dependent variable. Okay, You're just trying to find the estimate of contribution. Okay. So for example, you might have seen, different variables. Maybe sometime we call it a dependent. So for example, height of a plant. So that is depending on how much you put water, how much you put, let's say, fertilizer to the plant. So that these two things are independent variable, but dependent is height. Okay. Similarly, independent variable, if you see the liquid used to water each plant, that is independent of the height. Okay. So you you just know how to find out independent and dependent variable. And there is something called a controlled variable. Okay. So for example, if you are controlling the experiment, okay, for example, the type of plant you are using, the kind of, you can say, the pot size, the amount of liquid you are using, maybe it's a different, you can say, maybe some kind of pesticides, herbicides. Okay. So these are nothing but the controlled variable. You are just controlling it, how much you have to use. Okay. But in regression, we will only focus on independent and dependent variable. Okay. So for example, amount of water, okay, you are giving to a plant, and the growth of the plant. Okay. So it is depending on how much you are watering a plant. Okay. So independent and dependent, you have to understand before you formulate any regression analysis. Okay. Because whenever you formulate any regression related ML algorithms, you have to find it out what is dependent and what is independent variable. Because once you are able to find out the dependent and independent variable, you can easily formulate, let's say fx equal to y. Fx is nothing but it's a collection of all your input variable or all independent variable, and y is your output variable. It's just a relationship between y equal to fx. Okay. So mathematically, I'll show you what regression looks like and what is the equation of this regression line. Okay. So independent and dependent variable. So there is something called cause and effect. Okay, the causality. Okay. So what causes? If you are putting water to the plant is growing. Okay. So the cause is watering the plant, and the effect is the growth of the plant. Okay. So cause and effect is there. It's inbuilt in regression. So that is why in regression formula, it was the contribution, the effect of contribution of independent variable on dependent variable. It was written there in the definition. Okay. So we're just trying to find out the cause and effect. Okay. So that is why the dependent variable is the variable being tested and measured in an experiment, and dependent on the independent variable. An example of dependent variable is, let's say, depression symptoms, which depends on the independent variable, the type of therapy. Okay. So for example, if you have some certain kind of a depression, then you go through certain, let's say, XYZ kind of a therapy. Okay. A specific therapy. So cause and effect is there. Okay. So the causality part is there in regression. So just remember that there are also some causal effect on regression analysis. So independent and dependent variable will behave in certain direction. That is why it is linear. Okay. If it is non-linear, it will follow some polynomial graph. Okay. So coming to this simple linear regression, just see this one. x is your independent variable. So whenever anything you see on x-axis, it's your independent variable, and anything on y is dependent. Okay, so here you assume x is a sales data and y is revenue. Okay, and these are the data points. These are the data points. Okay, so if you plot it out and if you put this line, this red line, so this is nothing but this is called a line of best fit. Line of best fit. It is passing through every single data in the best possible manner. Okay, but still it is touching to some of the data but not all the data. Okay, it's touching majority of the data points, but not all the data points. Just see this plot, because this is something which is very interesting. If you see this this data, this is touching to this line of best fit, red line. This data point is also touching. This one is also touching. So there are quite a few which are touching and which are close to this line of best fit. Few are up and few are down. Okay. So now it's in linear regression. We just try to minimize the error. So a point, let's say this point is far away from this line. So how much far is from this line? We'll try to minimize it. So there is something called sum of a squared error. Okay. So in coming slides, I'll let you know how you can minimize the error. Okay, in linear regression. Okay. So it's just a line. So line of best fit is nothing but it's passing through the data points. Okay, that is called a line of best fit, because which will fall, which will touch few data points, but there are something called a residue which are not touching this line of best fit are called residuals. So this is a residual, this is a residual, but this is not residual because this is touching a line of best fit. This is not a residual. This is also not a residual because this is touching a line of best fit. This is also touching a line of best fit. Okay. So simple linear regression is a model that estimates the relationship between the one independent variable and one dependent variable using a straight line. Okay, as I already said, the line of best fit, it's nothing but a line of best fit. So if you go through the equation of a straight line, it's called y equal to mx plus c. Y equal to mx plus c. M is nothing but slope and c is intercept. So anything which is cutting on y-axis is called c. From 0 to this red line, whatever cutting on a y is a c, that is called intercept. So in simple linear regression, it's nothing but a line of a straight line equation. Okay. So y equal to mx plus c, as I already said, y is nothing but your dependent variable. Here, let's say it's a revenue. mx, m and x. X is your independent variable and its coefficient, we call it a slope, and this is c, that is your constant term. How much you can say the error part, that we can calculate through this constant term. There is also some error part also associated with this. So but normally we write y equal to mx plus c. This is line of a simple linear regression, you can say the line. And ultimately we have to develop through the data set, we have to develop this equation only, y equal to mx plus c and plus some error terms. This will come once you run in a Python or R. Okay, just remember that. So anything multiplied by x through independent variable is your slope, or it's called a coefficient. Okay, and this is a constant term. Okay. So if you see this visual, the constant term, the c part, is this one up to this. So the line of best fit is this and the c part is this. Okay, So that is why y equal to, this is b1 is m and x1. x1 is one independent variable. Coefficient is b1. b naught is intercept here, and e is error. So whenever you formulate any ML algorithms, there is always some errors associated with it. Not a single model will give you R square value of 100%. There will be some errors. So that is error terms. Okay. If you see this one, the slope of the line, if you draw a line like this, so this is nothing but b1. This line, this slope is nothing but b1, and this is intercept. Intercept is your b0, and this is your regression line, and these are some observed data. Whatever data is there, that is observed data, and the data falling on this line of best fit is your not a residue, and the data points which are falling away from this line of best fit is the residuals. Just remember that. Okay. So this is simple linear regression, and it's you can say the mathematical formula how you can calculate it. It's nothing but a line of a straight line, equation of a straight line. Okay. So equation of straight line, you have seen it. So there are different way to come up with the line of best fit. Okay. If you see this one, there are some data points which are here. Okay. There are some data points. If you see in this visual, the first one, the two data points are away from this line of, let's say this is line of best fit we put in. Okay, but these two lines are away. So this is not a good way of putting a line of best fit. At least line should pass like this. If a line should pass like this, we can still call it a line of best fit. Okay. If you see this one, this line of best fit, each point carries the same weight. Okay. So we have to manually, you can't do that, but as our data are maturing, as we are putting a lot of data, so through Python programming we can come up with a best line of you can say the best line of fit. Okay, line of best fit. Okay, so this will give you the equal distance from all the data points, equidistance, or may or may not, but at least it will minimize the error. Okay, so that your model will give you higher accuracy. Your sum of a squared error will be reduced and your R square value will be increased. So it depends on your line of best fit. Once you are able to find it out from where we can find this line of best fit, your model will give you a more correct, or you can say the high performance on a unseen data. Okay. So as I already said, the value which are away from the line of best fit are residual. So a point, let's say this one, on a positive side are positive residual, which are below the line of best fit are negative residual. So y and y cap. So y cap is something which you have predicted, and y1 is your actual data. So this we have to minimize, y minus y cap. We have to minimize it. Okay. So ultimately the line of best fit keep minimizing this, you can say the actual and predicted value. Okay. The line of best fit is the result of minimizing the sum of the squared of the residuals. So we will y minus, let's say y1 minus y1 cap plus y2 minus y2 cap. So there are, if you have many data points, it will just square it up and minimize the data points. So this will give you the line of best fit. Okay. So the error which I have introduced, the error terms. So y1 is the observed value, and this you can say the y1, y cap you can say the predicted value, y cap is a predicted value. So the error part, this one ei, if you square it up, it will give you the least square methods. Okay, so in the least square methods you are keep on minimizing the error, that is your observed and predicted value. The story goes on like this, and you are just adding it up, and this will give you OLS value, that is called ordinary least square value, which is nothing but it gives you a kind of, you can say, the predictive value of regression models, and it add up to the, you can say, the reduction of errors. Okay, so the least square regression is used to predict the behavior of dependent variable. You might have seen earlier or maybe in other subjects. In regression analysis, we keep on finding this ordinary least square, where we have some charts where we see some R square value. Okay, so the based on this R square value, also there is something called adjusted R square value. So these are nothing but this values give you an idea that how much your ML model is predicting correctly. Okay, it is in terms of some percentage. Okay, so there are some assumptions of this linear regression. So what are the you can say the assumptions of this regression? So whenever you formulate any regression model, you have to keep in mind that some assumptions is to be introduced, and before applying any tools and techniques, you have to assume something. For example, the first one is the independent variable should be linearly related to dependent variable. It means if I'm increasing the sales revenue, in case of this might increase. Okay, so every feature in the data is normally distributed. It means, let's say if you are calculating let's say the salary of a person, if there are 4 or 5 features, let's say age, income, educational level, something. Okay, so in that case you have to assume that every single features which is normally distributed, if you draw it up, it will follow a bell-shaped curve. That is your normally distributed data. Okay, and there should be little or no multi-collinearity in the data. So in this multi-collinearity, I'll show you in coming PPT sorry coming PPT, that how two variables, if they are collinear, how it can help spoil your ML algorithms, this regression, because the two variables will behave in the same manner. So you have to remove one. Okay, and the mean residual is 0. So the mean of the residual is 0. It means there are some data points which are away from the line of best fit. So our continuous struggle is to make the residual 0. It will not happen, but through this ordinary least square, you are trying to minimize it and making it to the 0. Okay, and residual obtained should be normally distributed. So even the residuals, if you plot it out, their graph would look like a bell-shaped curve. Okay, so these are some assumptions. So assumptions means typically we come across whenever we formulate this regression and you can say the analysis. So in that case, you have to check few of the assumptions. And there is something called there should not be little or no autocorrelation in the data. Autocorrelation means dependent and independent should be highly, you can say, no correlation should be there. If they are highly correlated, if two variables are highly correlated, it means the two variables are explaining the same thing. Okay, so these are the some assumptions. Okay, and this autocorrelation part will help you out how to reduce the number of features in your ML algorithms. Let's say if you have a 12 features and two of them are highly correlated, so you will remove one. It means only that. Okay, so mathematically how we can see how it works, this regression mathematically. For example, let's say someone has 2 years of experience and their salary is, let's say, 15,000, let's say. And similarly someone has 16 years of experience and they are getting, let's say, $90,000. Okay, something like that. So we have data points, and now we are trying to understand, for example, if a person, let's say, so 2, 3, 5, 13, these are some data points, 9 years. For example, if someone has, let's say, 20 years of experience, how much would be his salary? This is just a regression, you can say the objective. Okay, if someone has a 20 years of experience, then what will be their salary? Okay, so mathematically you can go and calculate it, but before that, so these data points, let's say this is your independent variable, year of experience, and year of, depending on the salary is depending on year of experience, so salary would be your dependent variable. Okay, just remember that this one. And this is nothing but simple linear regression because there is one independent and one dependent variable. Had it been more than a two independent variable, we call it a multiple linear regression because there are multiple independent variable and we have to find out the effect of those independent variable on dependent variable, that is your salary. Okay, so if you go through the mathematical way, we are trying to calculate the sum of a squared error. Okay, so here the yi is your dependent variable, that's your salary, and y cap is your independent variable. Okay, so y minus y bar. Okay, so 15 minus 14.44, so this is y cap. Y cap is nothing but its average, and we are just subtracting it and we will square it up. Okay, so we will get this sum of a squared error as 52226. It's just a maths. Okay, and how we are calculating the regression line, we are just trying to understand mathematically. Okay, mathematically sum of a squared error we got like this. Okay, and this is your y cap, and the formula is y equal to mx plus c. Okay, so for this there's something called OLS. OLS is nothing but your ordinary least square, and this is just a formula of a slope. So we will put everything which we have calculated mathematically and we will get a formula like this. If you bring this y here, y equal to mx plus c. This is just a simple way. Okay, so if you calculate it, the m, b and everything and put in the formula, you will get y equal to 4.80x plus 9.15. This is a c. This is your constant term. Slope is 4.80 and x is your independent variable, that is your experience, and y is salary. So let's say if someone has 20 years of experience, you put just multiply by 20 here and you will get the prediction. Okay, this is just a simple one. So in R programming, I am not running here the R programming, but I'll let you know how you can calculate. So here the same question is there. So you have to find the you have to find it out the linear coefficients, that is the value of x, okay, and the line of base fit, and how much someone will make their salary with 15 years of experience. Okay, so formula is there, we have calculated mathematically, but how we can calculate through the R programming. Okay, so here if you see, just see this one, YOE, year of experience. So someone has 2, 3, 5 up to this 9 years of experience, and salary was up to 54k. Then if you apply this, LM means linear model, and salary, and this tilde sign is the relationship of Y of E. Salary is dependent variable here, and year of experience is independent variable. We are saying tilde sign is a relationship. So in a linear regression, we pass this tilde sign. Okay. So whenever you just pass this formula, this programming, and summary LM is nothing but we are passing, we are saying the summary of LM. What is the summary of this linear model? So when you see this one, you will get something like this, this output. So YOE is nothing but it's a coefficient, that is the coefficient of year of experience. So we will multiply by 4.79, or we can say 4.80 into YOE, plus error is 0.426. okay. Or we can take, sorry, this intercept is 9.19 or 9.18. so formula would be salary equal to YOE multiplied by 4.80 plus 9.18. okay, this will be your formula. Okay, if someone has 15 years of experience, just we have to multiply 4.80 into 15 plus 9.18. This will give you a value of Y, that is your salary, if someone has a 15 years of experience. Okay, so this is how we can calculate it through the output of R programming also. Okay, and this is nothing but I'm just showing you the line of best fit. If you see, there is a one point which is touching the line of best fit, and every data points are away. So this is nothing but this is just a residual. Residual means data points which have some errors, which are not passing through the line of best fit. Okay, so if someone has let's say, so salary, how we calculated salary equal to 9.180, that is your C, plus YOE is nothing but year of experience, and then you will multiply by the coefficient, which we have got was 4.7996. so if someone has 15 years of experience, we will just replace YOE by 15 and multiply by this. So we will get a salary as a $18.1749 if someone has a 15 years of experience. So this is just a simple one. Okay, so R squared, that is something called R squared. Okay, so R squared value, I'll explain you when I'll show you through the Python programming. Leave it here, but R squared value, just see, means that the dependent variable cannot be predicted from the independent variable. Let's say if some let's say R square value is 0. Okay, here if you see the R square value here, just see the multiple R square value, this R square value is 0.95. it means your data points is explaining 95% variability in the data. Okay, 95% variability in the data is being explained. So that is something called R square value. If this value is too high, it means your model will give you higher accuracy. It means out of 100 prediction, your 95 times you will be winner. Okay, because their accuracy is 95%, which is quite a good one. Okay, so that is why this is nothing but a R square value. So how R square value, so R square value, so what is the significance of this R square value? So if R square value has, let's say, 0.99, means 99.1% of the variance in Y is predicted from the X. Just remember that. So these are the 2 points, just remember that. Others I'll let you know once I'll explain you through the Python, it will help you. But R square value is just explaining of the variance in the Y. Okay, just remember that, this one. If your model is giving R square value, let's say 10%, 15%, it means variability is less explained. Okay, just mute someone, someone is unmuted. Okay, so for data points, uh, for example, for multiple linear regression, if you have to predict the stock price, okay, so month, interest rate, unemployment rate, stock index price, these are the some, you can say, the independent variable here. Month, interest rate, unemployment rate, stock price. Arif, are you there? Arif, are you there? Am I audible? Hello, am I audible?
Yes, sir, you are audible.
Okay, whose mic is unmuted? Just check someone's mic is unmuted. I'm just removing this guy. Who is Hemdat? Who is Hemdat? Yeah, okay. So is my screen visible? Just confirm. I just got disconnected.
Yes, sir.
Okay. In between, just ask because I can't see you all. Sometimes it's like a monologue. So, okay. So, just see this data set of multiple linear regression. The stock index price is nothing but your dependent variable. Just see, because by looking at the data set, at least you will have an idea. This stock index price is your dependent, this entire. And the rest, this year, month, interest rate, unemployment, these all are your independent variable. And this last one is your dependent variable. So obviously this will fall under multiple linear regression. Okay. So how we are going to predict the price? So I have just used it in R, so don't get confused. I'll show you in the next class in the Python as well. Okay. So year is independent variable, month, interest rate, unemployment rate. These all are your independent variable. The last one is stock index price, your dependent variable. Okay. So if you plot it out, unemployment rate and this stock index price, you just see this is going down, stock index price. So this is nothing but this is showing a negative, you can say, the correlation, because unemployment increasing, this stock index price may be decreasing or increasing. Okay, so they are in the reverse direction. Okay, so scatter plot will give you an idea how your data is behaving and in which direction your data is moving. Okay, so in the R, if you people have run the R programming, this LM is nothing but a linear model. This is LM is a function, LM. Okay, it's a function. So stock price is your dependent variable and rest are independent. This interest rate, unemployment rate. We are just taking the two here. Okay. And we are running this model, linear model. So we are getting some estimates. So we are getting estimates of independent variable. So estimate of this interest rate is 345.5 is nothing but it's a coefficient, but we call it an estimate. And there are some errors associated with this estimate. Okay. And unemployment rate, their estimate is minus of 2.5.1. Okay. And these are some asterisk mark. If you see, these are two asterisk mark. These are significant. It means interest rate and unemployment rate has an effect on your stock index price. So that is why these two indent variable has a significant contribution on dependent variable, which is your stock index price. And if you see the R square value, multiple R square value, it's about 90%. It means this model is explaining the 90% variability in your data, right? From your this independent variable, that is interest rate and unemployment rate. That is how much variability is being explained, is being captured in R square value. Okay. So this is how, using only the output, at least you will have an idea what the analysis of regression models tells you. Okay. So this is nothing but your formula, intercept plus interest rate multiplied by what was the coefficient of this interest rate and the coefficient of employment rate and their intercept. So this will give you the formula. Okay. So if you add it up, the stock index price equal to 1798 from 0.4, which is coming from here. 1798.4, which is intercept. 345 of the, you will multiply by it, their coefficient, and unemployment rate coefficient is minus 2.50. Okay. So just see this one. So in formula we are just adding the coefficient. So a stock index price is 1798.4 plus 345.5 of this x1. X1 is nothing but interest rate, and minus of 25.1, that is unemployment rate. So whenever you increase, so how you are going to explain? So whenever you increase 1 unit of interest rate, if you are increasing 1 unit of interest rate, so a stock index price will increase by 345.5 unit. So in maybe in exams you can say, if this line is given, how you going to interpret it? So it means if you increase 1 unit of this unemployment rate, interest rate, your stock index price will increase by this much, 345.5. Similarly with your unemployment rate. Okay. So this is how we can explain whenever you see any output of regression model. Okay. So now this is done. So there is something called multicollinearity, which is very much important in this regression analysis. So multicollinearity is a condition where there is a significant dependency or association between the independent variable or the predicted variable. So whenever you see a term called independent variable, and they are also called predictor variable. Okay, a significant correlation between the independent variable is often the first evidence of presence of multicollinearity. So I'll explain you what is multicollinearity. Okay. For example, just see this one. This will help you understand what is multicollinearity and why you have to remove multicollinearity before applying any ML algorithm related with regression analysis. Okay. So imagine you went to watch a rock band's concert. There are two singers. Okay. just follow this line. There are two singers, a drummer, a keyboard player, and two guitarists. You can easily differentiate between the voice of singers as one is a male and other is a female. But you seem to have trouble telling who is playing the better guitar. Okay? Both guitarists are playing on the same tone, same pitch, and at the same speed. If you could remove one of them, it won't be a problem since both are almost at the same pace and tone. So this is very critical one. For example, in your let's say variable, let's say 10, 15 variables, if you have independent variables, out of that, two resemble same. Let's say a square feet of a room, an area of a room. So whenever you plot it out, it will have a high collinearity because they are reflecting towards the same thing. It's telling you this, it's telling you in the same tone, same pitch, and in the same speed, the area of the room and the size of the room. That is why we will remove one and we will retain one. This is how you can say the concept of multi-collinearity. So the benefit of removing one guitarist is the cost cutting and few members in the team. Similarly with the ML models, if you remove one, your predictability of the models will increase. Okay. So here both guitarists are collinear. If one plays the guitar slowly, then other guitarist also play the guitar slowly. If one play faster, then other also play faster. So it means they are more collinear. So you have to remove one. Similarly with the ML models. Okay. So removing one will help you out and removing this multi-collinearity. Okay. So I have shown you something called collinear, the matrix. Okay. So if there are some 5, 6, you can say the data, these features, and you have to find it out which features are highly collinear. Okay. Then you have to calculate some tables. Okay. This tables, you can say this is one, and you will see their contribution. Let's say outlet establishment year and item weight. Their collinearity is 52%. Okay, and others have less effect on that. So we will try to find it out whether we have to retain this variable or we have to remove. Okay, so this will help you in a correlation matrix. If some two variables are highly correlated, then we will remove one. Okay, and how we detect and remove multicollinearity. So there is some term called variance inflation factor corresponding to each and every independent variable in the data set. So it is always desirable to have VIF value as small as possible, but it can lead to many significant independent variables to be removed from the data set. Therefore, VIF equal to 5 is often taken as a threshold, which means that any independent variable greater than 5 will have to be removed, although the ideal threshold value depends on the problem at hand. So it depends on the business side of it. If it's medical industry, if it is too sensitive, then you will keep the variables, otherwise you will remove it. Depending on industry to industry, the variable, the variance inflation factor will vary. Okay, so if you see this variance inflation factor, so the highly correlated value is this WT versus DISP. They are highly correlated, that is 89%. Okay, the value is approx 90%. So we will remove one. We will keep either DISP or WT. So this correlation matrix will give you this some kind of a variable influence factor. But we typically go with this correlation because the correlation will tell you a lot of story about the variables. How two variables are highly correlated, whether they are highly correlated or not. Okay. So variance inflation factor, you can calculate it, but it's not desirable here. I'm just telling you why it is required to check the multicollinearity. Okay, but you can use it using only correlation. So variable inflation factor is not desirable here. And there is something called multiple linear regression. It's just extension of simple linear, which I have already explained. But here just see. So why is your dependent variable? So don't get confused if someone is saying you explained variable. Dependent variable is also called explained variable, response variable. So these are interchangeably used. So don't get confused. Similarly, independent variable, let's say here x1, x2 up to xk, these are independent variable. They are also called explanatory variable, regressor. So don't get confused if these terms are there. And there is something called error term, disturbance, unobservables. These are some the terms which are used for error. Okay, and this is your intercept. So in multiple linear regression, you have many independent variable. You will have obviously intercept, same as simple linear regression, and some error terms, because not a single model will predict you 100%. So obviously every single model will have some errors. So in multiple linear regression, how typically it looks like, for example, price, engine size, horsepower, peak, RFM, length, width, height. These are your x1 to x6. These are your independent variable, and price is dependent variable. So price is depending on height, width, length, peak, RFM, horsepower, engine size. Okay, and every single independent variable have certain estimates, which are denoted typically using the beta coefficients. So if you calculate price equal to using these estimates, so this formula will come. Okay, and you are multiplying through this estimates. So typically multiple linear regression and their formula looks like this. There are many independent variable and one dependent variable. Just remember that. Okay. Similarly, for a simple linear, price is depending on engine size, and let's say if calculated, and their estimates is the beta coefficients, and their price is, let's say, through some data points they have calculated price equal to, that is your residual plus engine size and their coefficient 156.9. and if you have a new data, let's say engine size is 20, you will multiply it and the price we can easily calculate. So this is how we can distinguish between multiple linear and simple linear regression. Okay. Now see this one, interpretation of this. If I give you this output only and I tell you to explain what is this. So here, what is dependent variable here? Okay. So here, if you see this one, dependent variable here, it is not written, but the intercept, engine size, horsepower, these all are obviously your independent variable, and their estimates, these are the coefficients, typically we call it estimates or coefficients. And the p-value star, whenever you see this star mark, it means they are significant. It means they have effect on dependent variable. So horsepower, let's say engine size, has higher effect on the price. The price was dependent variable. Okay, so this will tell you this star mark, the p-value. P-value, if you see this one, the value is, all p-values are less than 0.05. Only this value has some problem, more than 0.05. Otherwise all value are less than 0.05. That is why it is significant. You have to reject the null hypothesis. It means it has certain effect on the price of a wheel, let's say. Okay, so these are coefficients, and multiple R square value is 81%, 81.8%. It means it is explaining 81.8% variability in your independent variable. Your dependent variable is explaining 81.8% variability in the independent variable. So these are the sum terms. At least you know, whenever you see the output of any, you can say the regression, a line, or maybe the regression problem, at least you have an idea that what is going on. A simple, what all features you have to tap into, and you have to understand. Okay, independent, dependent, R square value, the p value, the beta coefficients. These are some important terms which you have to remember it, and at least you know how to explain. Okay. So which I have already explained this R. Okay. So you can see, and I'll share you this PPT, and you can see if you have any problem you can ask. In next class I'll show you through Python how you can run multiple linear regression and simple linear regression, and you will see their output, how we can interpret it. That is more important, okay, in business sense, because majority of the times you will not run a ML model, but majority of the time you will see the output, and you people must know, because you people are from the business side, so you must know how to interpret the output of any ML models, because ultimately you have to bring the insights out of the ML model. Okay, so this is all from my side. So if you have any question you can ask. Oh, 1 minute. Arif, are you there? Arif?
Yes,
There?
yes, sir.
Can you take a snapshot of attendance, because I don't have a pen here. So just a snapshot of this the people, and just send me. Okay, Arif?
Okay, sir, I'm taking it.
And let me know so that we can close the session.
Yes, sir,
Yes,
I'm
sir, I'm
taking it.
taking.
Okay, so thank you so much. If you have any question, you can ask. Otherwise, let me close the session. Okay, thank you.
Thank you,
Thank
sir.
you, sir.
Okay, thank you.